My talk is quite related to the very nice work that was presented just before me, but I wouldn't call that, as the session chair said, it's very same work, because I didn't spend nearly as 2.5 years on this. So you will see that obviously as my talk proceeds. So we look at the journaling of journal problem from a very different perspective, specifically from the perspective of implementation and configuration of file system journaling, unlike the previous talk that targets the database implementation at application layer. I'm Shen, and this is a collaborative work with Stan Park and Meng from the University of Rochester. Stan has since graduated, and currently he's with HP Labs. So by now you should be probably quite familiar with the journaling of journal problem from the previous talk. I'm just going to make a quick follow-up. We're looking at a situation where we have a lightweight databases like a SQLite and key value stores such as Kyoto Cabinet that manage the consistency of their own data over failures by enabling failure atomic I/O with the support of redo or undo logging. And these databases and key value stores run on file systems. So they store the database and logs as files. And as such, they further rely on file system journaling to protect the file system structure and metadata over failures. And here's a very simple illustration on the slide. It shows the application writes to a database file and a log file. And both files are also committed to the durable storage into the file system and also the journal. So this journaling of a journal situation is a pretty clear violation of the classic end-to-end argument in optimal database design. In particular, here you have one function, the function of failure atomic data protection, that's implemented in two places, at both the application layer, in this case the database, and also the operating system layer. So if you implement one function at two different places, you tend to be inefficient and hurt performance. And indeed, we run our experiments of adding the ext file system journaling to the SQLite database. We saw up to 73% slowdown of the transaction completion time. This problem has been looked at in several recent studies. There are some existing solutions to it. One was to use the log structure file system to replace the journaling completely. The other was to put a file system journal on an external device. And the work that was presented just before me presented new database storage layout so that it can sync less frequently and therefore improve performance. And these techniques are very effective in their own right, but they tend to require substantial changes in system layout and quite substantial application changes as in the work that was just presented. And so we look at the solution to the problem from a different perspective, from the implementation and configuration of file system journaling. The additional costs of adding file system journaling to these applications are primarily due to the additional I/O operations and larger I/O size written to the storage. The fundamental result, the main results of our work, is that we think these additional costs are not fundamental. And the observed cost of adding file system journaling to these applications in practical systems is primarily due to the artifact of insufficient implementation or configuration. And they can be, these costs can be substantially mitigated with very simple implementation and configuration adjustments. And there are two specific simple enhancements we're looking at in the paper we have. One is to minimize the number of device writes on the transaction commits synchronous path. And another method is to enable adaptive journaling so that each file can have its own journaling mode according to its specific I/O access pattern. And that we found to be particularly applicable to redo, undo log files for lightweight databases. And one thing I want to emphasize here is that the goal of our work is to utilize very simple methods to highlight there's a different way of addressing the journaling of a journal problem. I wouldn't really intend to propose the best file system journaling optimizations. We have cited several nice work, recent work on optimizing file system journaling in our paper, and if you're interested in those, you can find them in our paper. So the first simple method we'll look into is to try to minimize the number of device writes on the journal commits critical path. And this would get better efficiency because fewer device writes means less management costs, both in software and also in hardware. This, in theory, can be easily accomplished by leveraging the full data journaling, in which the data and the metadata of a transaction are journaled synchronously, and this is done in a continuous write, and it can be done with a single device write. And data and metadata will still need to be checkpointed to the file system locations, but checkpointing can occur asynchronously at a later time. And in fact, they may never have to be done if the data or file in question is actually overwritten or deleted soon. But in practice, when we actually enable the full data journaling, you may observe that there's still more than one device write on the journal commits critical path. And one problem we notice is in the sync file implementation of the ext4 file system is sometimes checkpoint dirty data on the critical path of the commit unnecessarily. The particular symptom we saw is that if you have multiple fsyncs on a file, the delayed checkpoints of earlier fsync will be included in the critical path of a later fsync. And this we believe is not necessary for the correctness, and it can delay the response for the application transaction completion. And this can be easily fixed after discovery. So data journaling can help minimize the number of device writes, but they tend to write in a very large volume. It turns out that this is primarily due to the page granularity journal records in systems such as ext4. Basically, if the application makes a small write, there's going to be a journal record created for it, and that journal record has to be at least a 4 kilobyte page. In one particular example, we show in the paper, we had one transaction that makes, I think, 9 small writes. And these writes add up to a few kilobytes of total volume of writes. But they created 11 whole 4 kilobyte page on the journal. That is 44 kilobytes. So that's an increase of more than a factor of 10 in terms of write size. So this large write size incurs high cost for writing on flash, and also they increase the wear and reduce the lifetime of the flash device. And in this, we try to leverage existing journaling techniques, or at least the ones that are being proposed to address this issue. A particular nice idea we looked into is the so-called adaptive journaling that was proposed back in 2005 by researchers from Wisconsin. The idea is that you can let each transaction to have its own custom journaling mode so that it provides best performance for its particular I/O access pattern. In particular, if the transaction would already perform sequential I/O under the ordered journaling, there's really no need to turn it into a full data journaling for the purpose of minimizing the number of device writes. This is a very nice idea, but there's some implementation issues if it's not done properly. In the case of overwrites, in particular, between transactions, a failure-triggered recovery can lead to a reordering of writes improperly between the transactions. Here's a very simple example. If you get 2 transactions, T1, T2, in the order, that overlap in their data writes, and if T1 does a full data journaling that includes both the file data and the metadata on the journal, and T2 instead shows metadata-only journaling, and if you have failure that triggers the replay of the journal log, T1 would reapply both the file data and the metadata from the journal. But T2, because only its metadata is journaled, so it only has its metadata reapplied. And this will leave T1's data write as the final state on the file system, which is wrong because T2 is supposed to happen after T1. There are multiple ways to address this, and in the spirit of looking for simple enhancements, so we use a very simple approach, that is to make the adaptive journaling more coarse-grained. Specifically, we set custom journaling mode on a file-by-file basis instead of a per-transaction base. Therefore, all the transactions in a single file would use one journaling mode, so that overwrite problem that I just described would be mostly eliminated. This is also easy to implement because a lot of machineries that are already in the ext4 file system that can be leveraged to accomplish this. There's one concern in terms of the cost when switching journaling mode. For safety, you will want to flush all the dirty data, and we can mitigate this by basically setting the journaling mode at the file open time when there really isn't any outstanding dirty data. And if we only do that, then the cost of mode switching really doesn't exist. A coarse-grained adaptive journaling, like our approach, tends to be less powerful, but fortunately, it turned out to be quite effective for the journaling with journal situation that our work targets. Particularly if you look at SQLite database, there are two common kinds of logging that it does. One is a redo log, particularly the write-ahead logging. The write-ahead log is written sequentially with very little metadata changes. So such transaction commit is already a single sequential I/O under the ordered journaling, so there's no need to turn it into a full data journaling with larger size. On the other hand, the rollback-recovery log is an undo log, and this log file is actually often deleted or truncated after transaction commits. So every transaction commit would involve a quite substantial amount of metadata changes. And if you use ordered journaling, there will be multiple device writes, and that's less efficient. So it's preferable to use data journaling for those log files. Before I turn into the performance evaluation, I want to make a quick note on the applicability of this work. The recent journaling with journal studies mostly target smartphone workloads on Android systems. Following their footsteps, we tried to run some of these experiments, but unfortunately, our own experiments found that the typical smartphone workloads are much more dominated by the network delay. Even if when they use Wi-Fi, the internet round-trip delay can still dominate the local I/O storage latency. It's easy to see because round-trip on the internet can easily take dozens of milliseconds or even more, and a write to a local eMMC storage is often just a single millisecond. So we don't really claim that this journaling with journal problem is really critical for most smartphone workloads. Obviously, the I/O optimization only matters when the workload's performance is substantially affected by I/O activities. So we target general I/O intensive workloads on both server and client systems. Here are evaluations. We look at evaluation of we're running some insert, update, delete transactions against the SQLite database. This experiment is done on the conventional machine with Intel 311 solid-state storage, and we compare the case when SQLite runs on the ext file system with no journaling, with the order journaling and data journaling. And also we have our enhanced system in the comparison as well. And what we find is that compared to no file system journaling, the ext4 order journaling incurs up to 19% slowdown, and data journaling incurs up to 58% slowdown. And our enhanced implementation incurs actually no cost. In fact, it often improves performance because it merges multiple device writes into a single one. We also ran experiments on Nexus 7 tablet, but in this case, we're not really running Android. Instead, we just run Ubuntu Linux on it, and we run the same experiments, and we'll find very similar results. The order journaling of ext4 incurs up to 20% slowdown, and data journaling incurs up to 73% slowdown, and our enhancement incurs very little cost in comparison. So here is a conclusion of this work. Our main conclusion is that for applications that protect their own data, like these lightweight databases and key value stores, there is a fundamentally little cost of adding file system journaling to them. The kind of costs you see in a practical system are primarily due to the artifact of the implementation or configuration of file system journaling. And we're looking to some very simple enhancements in this paper we did, and there are actually more sophisticated techniques that we have cited in our paper that could even further improve the performance of file system journaling. I want to end this talk by mentioning one alternative approach to enable data protection. The main problem with journaling with journal is that you have one function that's protecting data over failures done at two places, at both application layer and operating system layer. So the alternative approach is to let OS to expose failure atomic I/O API, and then have the OS alone to protect the consistency for both application data and the file system structure. And one direction along this approach was some nice previous work that proposed transactional I/O API to applications and have operating systems to support transactional I/O. A work we did last year, presented at USENIX, was to enhance the POSIX msync semantics with failure atomic support so that applications can express their failure atomic semantics, and then it can be implemented in operating systems together with the protection of file system structure. So under such an alternative approach, the data protection is done in one place, operating system, which tends to be more efficient, but it requires operating system API changes and programming changes. So this is the important trade-off that will have to be carefully evaluated by systems and application developers when we search for the best way of protecting data as we move forward. And this concludes my talk. Thank you very much.
We have time for a couple of questions. And the microphone's on two sides of the room.
Hi, Ted Wong, Illumina. Just for the fun of it, what would happen if you just turned off all the journaling in the file system? You know, run against CXT2. Wow, okay, that's 3. 2. Fat.
Well, in theory, if you do that, then if you have a crash, then you will need to, your file system may not be in a consistent state. You have to run file system check to recover it. And you got Ted Cho sitting next to you, so he will know much more on this. What will happen in practice when that's the case? Yeah.
Right, but the question is really, you know, the database makes some very pessimistic assumptions about the way in which the file system is going to behave, right? So assuming that you don't lose too much during the crash.
Yeah, so I do have to, in this case, I guess what will happen is the database only protects, its data if the files are preserved in the way they're supposed to be preserved. So if you have a complete file system consistency problem where files are not even recognized, for example, then the database has no way to recover. It doesn't even see the log file, for example. How could it recover its data, right? So in that sense, you do need two protections, both for application data and for file system structure for full protection.
All right. Thank you.
Yeah. I think that was a good point, because I think what is the interesting comparison is to do what enterprise databases traditionally do. That is, you still have your journaling file system underneath, but your actual file data is completely pre-allocated. And I don't actually mean pre-allocated, but zeros or initialized with a pattern. And now if you have a traditional file system that does not do copy and write operations on every write, you essentially do not journal anything because metadata does not change. So that would be the interesting comparison, if that is actually practical for these kinds of mobile workloads or the key value stores you're working
so that's a very good point. If you think about it, the problem with journaling with journal is that you have one function that's done in two places, a database and operating system. And there are really two ways of trying to turn that around. One way that I said in my talk was that you can get everything done in the operating system. But when the end-to-end argument was first argued by Stonebreaker, he actually argued that just get rid of the operating system and actually do everything in database, which is what you said. That's some of the enterprise file systems do. But the point is, for a lot of, I guess, lightweight applications that do data management, it's too complex to have them to manage the raw device directly, so they tend to run on file systems. But that is a valid approach, especially taken by the enterprise systems.
And by the way, I really like your paper about the atomic msync, and I'm looking forward to talk about it at LinuxFast later and actually make it reality in production.
Thank you very much.
Peter Desnoyers, Northeastern. So I'll turn around a bit of what some of the previous questions said, and given that for Android, probably the predominant failure to protect against is dropping your phone and having the battery pop out. In fact, catastrophic crash is a frequent occurrence. So do you see any ways in which these changes actually either reduce or increase the opportunity for inconsistency?
That's I can try to comment as much as I can. So the one assumption with all of those data protection over failures assumes a fail-stop scenario where when you fail, you stop the system, but then whatever was done before the failure was still preserved on the storage. And that's the assumption we make as well. And I also actually said in my work that we don't specifically target Android systems in any way. If the particular Android video model follows the fail stop model, then our result will still apply, but otherwise you may not. I guess that's as much as I can comment on that. But thank you for the question.
Okay, thank you. Yes, and I think that applies to what's there right now too. So,
Thank you very much.